Whenever you have any sort of first-order linear differential equation, you can use the variation of parameters technique to find a solution to that differential equation. In this video, we'll look at how we can use it to solve a first-order linear differential equation by looking at how it's related to the integrating factor. But I want to emphasize the fact that variation of parameters is widely used for higher order differential equations. So let's use a variation of parameters to solve this first order linear differential equation. And the first thing you have to note about variation of parameters is that in order to use it, you need to have at least one part of the solution in mind. So what do I mean by that? Well, in the case of first order differential equations, you need to have at least the homogeneous solution in order to use the method. So let's try to solve the homogeneous equation. So when b of x is equal to 0. So I've already made a previous video on how to solve first order homogeneous linear differential equations. But to quickly recap, what you essentially do is you separate the variables and then you integrate. And the answer will give us that the solution to the homogeneous equation is k e to the minus the antiderivative of our function a of x dx. So now we have one part of the solution, which is the solution to the homogeneous equation. And in technical terms, this is called the complementary function. And you can think of it as a part of the solution. So even though it's not a solution to this differential equation, to the non-homogeneous equation, it gives us a complement to that solution. Furthermore, we have a first order differential equation, so we know we need to have 1 degree of freedom, which is given by this constant over here. Now all is left to do is finding the particular solution to this differential equation. And now that we have a part of the solution, we can now use the variation of parameters to determine the second part, in other words, the particular solution. But the problem is that we have no idea how the particular solution might look like. So what we do is we use this part of the complementary function. And what we do is we vary the constant over here. We turn this constant into a function. And this is the idea behind variation of parameters. Parameters here basically means a constant. Okay, so that's why I prefer the term variation of the constant. So we turn the constant into a function. And then we basically try out the solution in order to determine the conditions that k of x this time, has to satisfy. So I've turned the constant here into a function of x. And the reason I do that is because we don't have a clue about how a particular solution to this differential equation might look like. So what we do is we use what we already know and we turn the constant into a function. So we vary the constant, we vary the parameters, and we see if this trial solution that we have might actually give us information about a particular solution to this differential equation. So let's plug this trial solution into a differential equation. So we know that y prime, using the product rule, will be k prime times e to the minus capital A of x, where capital A of x just designates the antiderivative, plus k. Well, now we need to differentiate this antiderivative over here. So it's just the function itself, a of x. But since we're taking the negative antiderivative, we need to put a minus sign over here. So we have minus k of x and times e to the minus capital A of x, or capital A of x is just the antiderivative of a of x. So now we plug in our trial solution into the differential equation. So we get y prime plus a of xy, which is just a of x times k of x, or k e to the minus capital A of x is equal to b of x. And the great thing here is that we notice these two terms cancel out. So essentially what we get is k prime e to the minus capital A of x is equal to b of x. And therefore, k prime of x is b of x times e to the positive antiderivative of a of x. And integrating on both sides, we get that k is the indefinite integral of the product of b of x and e to the capital A of x dx. So now we know the condition that the varying constant has to satisfy. In order for this trial solution to satisfy this differential equation, k, well, let me specify that it's a function, k of x, has to be equal to the integral of the product b of x times e to the capital A of x dx. And therefore, our solution to the differential equation is y is equal to e to the minus capital A of x times, well, k of x, which is the integral of b of x, e to the capital A of x dx. Now, there's one important point I want to make. This is an indefinite integral. And whenever we take indefinite integrals, there's always a constant associated. And since this is a first order differential equation, what we realize is that if we take into account the constant, the integral constant, when we compute this indefinite integral, well, then we actually get a general solution to this differential equation. So what we just realized is that y, our trial solution, is actually the general solution to our differential equation. And let me show you why. Initially, I said that we're trying to find a particular solution to this differential equation since we already have the complementary function. And so we can't have any constants, any degrees of freedom associated with the particular solution. And therefore, we can't take into account the constant when we compute the indefinite integral. So let's imagine that we don't take the constant. Okay, so we just evaluate essentially the antiderivative of b of x e to the capital A of x. So our general solution, yg, well, is just our particular solution plus the complementary function. So plus k e to the minus capital A of x. And now let's take the common factor, so e to the minus capital A of x. So we notice that we can factorize by the exponential over here. So we get the antiderivative b of x e to the capital A of x dx plus k. So if we imagine that this is a particular solution, well, then we have to add the complementary function. But the complementary function just gives us a constant over here when we evaluate the integral. So what we realize is that if instead we compute and we don't neglect the constant, so we take into account the constant over here, we get the general solution. So actually, the variation of parameters gave us the general solution to our differential equation, if and only if we're taking into account the constant over here. If we don't take into account the constant, well, this would just be time consuming because we add the particular solution and we add the complementary function. And just this would give us the constant that we would have initially had if we computed the indefinite integral. So this is the general solution to our differential equation. And we got that using the variation of parameters. But I made another video about the integrating factor, which is also a method used for finding the solution to a differential equation, a first order differential equation. And if you recall the formula for the integrating factor method, well, we realized that this is actually our integrating factor, e to the capital A of x. And this is actually 1 over r of x. And therefore, we realize that the variation of parameters actually gives us the result that we would have had if we used the integrating factor. So in the case of first order linear differential equations, the variation of parameters and the integrating factor are two sides of the same coin. They give us the same result. And one final point I want to make is that initially we were just trying to find one particular solution to the differential equation because we already had the complementary function. But what we realized is that the variation of parameters actually gives us a general result to our differential equation.